Good morning to all of you. Welcome to this session on design of channels placed back to back. Now it is a design of a built up column for heavy loads. Already in the previous video you have seen the design of two I sections joined together by a single lacing system. Now in this session let us study about how to design the single lacing system for the channels placed back to back as shown it here. The lacing systems will be generally provided for eccentric loading system, whereas the battens will be provided for the axially loaded columns. Now in this session let us try to understand and design the different components like the members, this built up members as a whole, the lacing flats and the joints. Here the joints have been designed with bolts of different grades. In the next video let us try to learn the same two channels placed back to back with the welding system for the same single lace system. Let us go with the welding. Let us study that in the next coming video. Now in this section we are going to design the flats in the form of the lacings in the form of flats. In the coming sessions or the coming videos you can observe how to design the angles and channels as a lacing system. Let us learn that in the forthcoming videos. Let me take a typical example to design the channels placed back to back. We can also learn about channels face to face or toe to toe. Channels face to face can also be called as channels toe to toe. Now in this problem we have got two channels placed back to back to carry a factored load of 1300 kilonewton, which has got an actual height of 7 meters and has been effectively held in position at both the ends but not restrained against rotation. The meaning of this is it is hinged at both the ends. Let us try to take out the effective length formula from the code and learn about that. And we have to go with a single lacing system with a 16 mm dia 4.6 grade bolts. So let me take the I section. I just place it like this back to back. We want to find out the suitable spacing for this, and all the spacing, everything will be designed based on the condition that we have to design with an economical section that can be obtained only when I take up the RZZ value which is running perpendicular to this web and parallel to the flats lacing. That one should have a minimum radius of gyration or less radius of gyration than about YY axis. That is what the code specifies. We have to purely stick on to that and see that how to design. I will speak about all these things in a separate video where the complete procedures we are going to talk about for the different conditions. You can look into that video and learn more about the theoretical aspects of these problems, how to solve the problems. Now you got the area of the two channels that is required to be found out by using the formula factored load divided by permissible compressive stress. The compressive stress could be assumed between 125 Newton per millimeter square to 200 Newton per millimeter square, approximate range from 0.4 times of Fy to 0.7 or 8 times of Fy value. The lambda value you can assume like that and get the stress, or assume the stress itself and solve the problem. I can assume anything between this and try to solve the problem. Now in this case I have taken the permissible stress as 125 Newton per millimeter square. The area required is 104 centimeters square, and we will read in terms of centimeter square because in the code ISSP 6 part 1 code or referring the steel table we have to look into the centimeter square. So we are going to convert the millimeter square to centimeter square. So the condition lies here for the lacing. As I explained earlier, the maximum radius of gyration RYY should be greater than RZZ. RZZ is nothing but the axis which passes parallel to the lacing system. So this is the layer the lacing has been done to the flanges of the channel. Now this is the XZZ axis parallel to that. That means RZZ should be less than RYY. Should be less than or equal, you can say. And the moment of inertia about ZZ axis and YY axis should be approximately equal. That is another condition to be satisfied, and based on that we are going to find out the spacing between this from the steel table itself or from the code book. So it has to be chosen from the steel table based on this condition. IZZ should be less than or equal to, nearly equal to IYY, and RYY greater than RZ. That is how you have to select from the table. Now we will take out the table, or what is mentioned here in the steel table, where the two channels are being joined together either by lacing system or by the batten system. So there, for the area that was required, we are going to refer, and that approximately 15 to 20% more we are going to take, and the area I am going to refer is 107.32 centimeters square. Now here I am going to look into the spacing in such a way that the moment of inertia about ZZ axis is approximately equal to moment of inertia about YY axis. These values are approximately equal, and at the same time the radius of gyration about ZZ, that is this value, should be less than the radius of gyration about YY axis. This is how we are going to select the member. So the selection of the member is ISMC 350, and the spacing for this is correspondingly equal to 220 mm. The distance between the channels back to back or from web to web we can call is 220 mm. We can try this, or otherwise there is other way of calculating it. We can calculate from the knowledge what we have got in the first semester of the engineering, that is from the moment of inertia chapter. We can do like that, or get it from the table itself directly like this. Any method could be adopted for selection of the section. Now we are going to try this section of ISMC 350 at 220 mm center to center. Now let us write down the section of for this properties, whatever we have got. The area is we have taken, the RZZ value I have noted from the table, whatever we have referred. I could have written also the value of IZZ and IYY, but since we are not using anywhere, I have not written here. If you want, you can write down that also. Now as per the page 48 of the code IS 800, the slenderness ratio has to be taken from the clause 7.6.15 as 1.05 times KL by R minimum. So R minimum is the minimum value of these two things, that is RZZ, we will note on that, and KL is the effective length. Effective length can be obtained from the table 11 of the IS code 800 2007, where the condition is given as that both ends are being restrained and free at the other for the rotation, means it is hinged at both the ends. For the hinge condition, the effective length is taken as 1 times the actual length. So whatever the actual length that is been given, that is 7 meters, the same 7 meters will be taken as the effective length. So this is what we are going, this is how we can write it, both ends are hinged. Now I got the effective length. Get the slenderness ratio lambda of the built up section. The lambda of the built up section is 53.81 with respect to the ZZ axis. So for this lambda value, you have to get the compressive stress from the table, and from the page 44 table 10 we can get the buckling class of the built up section. For any built up member, now here only I sections have been, doesn't mean that all the sections should be given. We have to look into this built up member. So built up members of any type, channels either back to back or face to face or with I sections or with angle sections, you are going to look into the buckling class of C. So the compressive stress you are going to refer is from page number 42 of the code, where it's given for buckling class C. That is, from table C you can get the value of FCD. So let us have a look on the table. This is an extract I have taken from the IS 800 code. Now we got 50, around 58 point something is the lambda the value. It lies between 50 and 60 here. KL is nothing but the lambda value, KL by R, lambda ZZ. This is the FCD value. We are going to refer it for yield stress of 250 Newton per millimeter square. For 50 it is 183, for 60 168. You are going to enter that. Now try to get the value by interpolation, where already you know about how to interpolate this. The difference of this and this is 10. The value for 50 it is 183 and for 60 it is 168. The difference is 15. For 53.81, what is the FCD value? It should be less than 183 and greater than 168. Let us get by interpolation. It's 177.03 Newton per millimeter square. From the strength of stress and strain concept, we know that strength of any material is equal to stress into area of that material. So load carrying capacity of this section you can find out by multiplying the stress, compressive stress, whatever you got for this members, into area of that two members. It works out to be 1002.8 kilonewton, which is greater than 1300 kilonewton. It is safe, but maybe uneconomical. So when you are designing, keep that this value should be either 5 to 10% greater than this value, so that it gives an economical section, or the cost will be more. Therefore, you can redesign it, but anyway I have gone with the procedure of solving the problem. Once it is start designing it in lifetime or for the field condition, see that this value is very close to this and greater by 5 to 10%. So you can choose a section which has got a lesser value of stress and the area, so that it comes to 1300 kilonewton. So once the section we have designed is safe, we can provide that. As I said earlier, it is uneconomical, but still no problem from the procedure of solving the problem from the examination point of view. Now let us design the flats here, lacing flat. So as per the code specifications, clause 7.6.8, you have to design the end plates. This is an end plate to be designed. I will design this plate, the length, the depth and the thickness of this section in the last part of this session. In my earlier video I have not designed that. Now I am designing it. You can have a look on this one. You can learn it. If you are interested, you will solve it in the exam from the examination point of view, or else no problem, but very much necessary from the life point of view. Check for local buckling of the section. According to the clause 50, page number 50, clause 7.6.5.1, we have to design this in such a way when it is these columns are placed and loaded, it should not buckle like this. There should not be any bend in the lateral direction. It should not bend. Therefore, to keep them in positions, we are going with the lacing battens, flats or battens, and see that these columns are kept in position. We don't want any buckling of the column to take place. So by providing the suitable flats, Let us make a check whether what we provide due to that, whether this column is going to buckle or not. Let us make a check. So that can be done by providing the lacing. I am going with a single lacing system here as per the question. In the coming videos, we can have a look on the double lacing system, the welded design of weldings and other things. So according to the clause 7.6.5 of the code, the maximum spacing, that is the distance between these two bolts, that is called as A1, divided by R1 is the minimum radius of gyration of a single angle section, shall be less than 50 or 0.7 times the slenderness ratio of the unfavorable slenderness ratio of the whole member. That means whatever the lambda you calculated earlier with 53.81, so that one should be multiplied with 0.7. See that value is not greater than A1 by R1. So now let us get the A1 value. Now if you observe this figure, in my earlier video where the two eye sections were joined together, there we had overlapped this lacings. There was only one bolt at one side, one bolt was there, this was overlapped. So we had a double shear when we were calculating the number of bolts in shear. But in this case I have changed a little bit, we are placing it side by side. The problem with this is it will be costly, that is you have to make a whole additional holes here and go with an additional bolts. Anyway, from the practice point of view I am going to teach you this. Let us try to understand this one and the approximations that we are going to make for this condition, this type of connections. Only from the academic point of view, to learn the subject I have just changed this. Now let us take the angle of inclination for this one, where the lacing battens should lie between 40 degree and 70 degree. The angle of inclination is what it is going to make with respect to the longitudinal axis shall be between 40 degree and 70 degree. This has been designed based on the economical design of the condition that this should not be too slender or should not be too flat. I will speak about all these things in a separate video when I going to talk about the design procedures of the different components as well as the lacing system and the bolted connection in particular. Now we are going to assume an angle of 45 degree. So there for this, from the steel table with a single eye section, we can get the value of the gauge length. The distance from here to the bolting position is called as a gauge length, that you can observe it here. So this is important to get the length between the bolts, horizontal length. So refer here for ISMC 350, the G value has been given as 60. So let us adopt the 60 mm distance to get the horizontal length between the bolts. You have plotted here. Now get the minimum radius of gyration, that is R1 required for the single angle section. Referring to the single angle section of the steel table, the radius of gyration about ZZ axis and Y axis. Every time I am reading XX as ZZ, remember it. So for ISMC 350, you got two values, 13.66 and 2.83. Out of these two, 2.83 centimeter is the lesser value. Therefore, R1 is taken as 2.83, that is 28.3 mm. So once you know this, get me the value of A1. Let us see the approximations that what we are going to make. The horizontal distance is this LH. And we know the spacing between the channels webs, it is 220 plus 60 will get me the LH value. Works out to be 340 mm. Now we know that tan theta is opposite side by adjacent side. This is the tan theta, opposite is this one, adjacent is this value. So if I get this heights, then I can easily get A1. So that is nothing but LH by LV, opposite by adjacent side, and LV is 340 mm, same, because if you have taken 45 degree it remains same. If you have taken any other degree you would have got a different value. So from here to here it is LV, the same way it is also from here to this bolt is LV. There is a gap here. This you can assume it equal to the thickness of the flats that we are going to assume, maybe around 50 or 60 mm we can take, and we can assume this, add up to get the value of A1 LV plus the sum 60 mm plus LV will get me A1, or you approximate this equal to A1 equal to 2 times of LV and neglect this part, and I can do like that, no problem, because none of the books have given very clearly about this. We are making an approximation there. If I am interested I can take up with additional length of 60 mm here, 50 to 60 mm, and add up to this LV plus LV, that is 2 times LV, and get the value and approximate it. Kindly note down this. So I have got the A1 value. A1 by R1 is 24.03, where it is less than 50 as per the code specification and less than 0.7 times the slenderness ratio of the built up section. It's 0.7 times of 53.81, which is equal to 37.5. Out of these two, the minimum is this. Whatever the ratio I got, the slenderness ratio A1 by R1, 24.03, is less than 37.45. Therefore, safe if I provide a single batten system with an angle of inclination of 45 degree, this is not going to buckle as it was explained earlier. It will not buckle, it will stand still and take up the load of 1300 kilonewton. So therefore, you can provide this single lacing system. I can adopt it. Now let us go and design the flats here. Now I said this session I will be talking with respect to the flats. In the coming videos let us learn how to design with angles or channels, I sections or tubular sections like this. Anything could be designed. We will see that in the forthcoming videos. Okay. According to the clause 7.6.2, the width of the flat, that is this one, shall not be less than 3 times the nominal diameter. Nominal diameter has been given by the examiner in the question paper. It is given as 16. Therefore, we are going to take that 3 times the 16, it is 48 mm. Say the width be equal to 50 mm. Thickness of the flat. There is a thickness to be taken. According to clause 7.6.3 as given in page 50 of the code, it states that for the single lacing system, it shall not be less than 1/48 the effective length of this lacing. So 1/48 of the distance of the inner to inner bolt's length. That means you have to calculate the length along this direction. So we know that sin theta is opposite side by hypotenuse. Opposite side is LH, hypotenuse is this one, that is L effective. I am going to designate this as L effective. So from this you can get the value of L effective. It's 480.83 mm, this length, or these are the simple trigonometrical ratios we have found out. So and substituted in the formula and got this as say 12.08, and if you refer the code book or the steel table, you don't have the next nearing number, you got a 12 mm thick flat is there and the next number is 16. Therefore, I am going to try a flat of 50 by 16 mm thick flats. So as given in the steel table, I am going to refer into this. So I am going with 50 ISF 16. 50 is the width of the flat, ISF Indian standard flats of 16 mm thickness. This is a flat which is having 50 by, I can name it here also. For the double lacing system, as it is stated there in the clause 7.6.3, it shall not be less than 1/60th of the effective length between the bolts. We will see that in the coming videos. Now whatever the flat you have designed, that should be, so it should withstand, and see that the slenderness ratio doesn't exceed as per the code given in the clause 7.6.6.3, where it states that the slenderness ratio lambda shall not be greater than 145. If it is a welding system, we can go with 0.7 times of that length, and if it is a double lacing, 0.7 times of the effective length. Now let us calculate the minimum radius of gyration, R minimum for this flat. After calculating this with the radius of gyration formula, it is equal to T by root of 12. So L effective is divided by T by root of 12. It is equal to, lambda is equal to L effective into root 12 by T. You can directly remember this formula, or this could be found out, there is no problem. So the lambda is equal to 104.10. So whatever the lambda you calculated, for this you find out the stress from the steel table. This flats will be subjected to both the compressive force and the tensile force. So lambda is less than 145, safe, there is no problem. To make a check, similar check with respect to compressive force, tensile. So how to calculate the force in the lacing bar? This is the tensile stress, this is the compressive stress, force developed in the flat. I can speak with respect to the force rather than stresses. So for this we have to make a check. This member, the force in the flat has to be calculated with respect to the transverse force that will be calculated from the longitudinal loading. The load will be acting along the axis of the member. You are going to find out the transverse force Vt, which is equal to 2.5% of the axial force of the member. The factored axial force is 1300. Take 2.5% of that, and that is equal to 32.5 kilonewton is the V2 value. Resolve this force along the axis, along the flat, and get the value of F. So sin theta is equal to opposite side by this hypotenuse. It is equal to V2 by F, where N is the number of shear planes. Shearing will take place here, shearing will take place here. We have to divide this, distribute on either side. All these flats will be placed with mirror image. So it will be distributed in two planes. Therefore, the force in each side has to be calculated. For the single lacing system, you have got one shear plane here, another shear plane. Therefore, the value of N could be taken equal to 2 for single lacing, equal to 4 for double lacing system. In this formula, the value of F is equal to V2 by N into sin theta, that is below the, it's in the denominator position. Get the value of force in the member, and that is equal to 22.98 kilonewton. This is a force in the flat. Let us find out from this force the compressive stress and the tensile stress. Compressive stress from the table 42, table 9C, page 42. You can get the value of compressive stress for that lambda value, which lies between 100 and 110. So for 100 it is 107, for 110 94.6. By interpolation, get me the value for 104.1 lambda value. Cross multiplied, get me the value of that question mark, and from that value will be deducted from 107, because it is going in the decreasing order. As the lambda increases, the stress decreases. Therefore, we are going to minus it here with respect to 107. It's 101.92 is Newton per millimeter square is the compressive stress developed in the flat, and that is, we have to find out the force in the member, and that is should be greater than the F value whatever we have calculated. Yes, it is greater than the F value we have calculated. Therefore, it withstands the compressive force. Now it is safe with respect to the compressive force. Let us calculate similarly with respect to tensile force, where the tensile force will be calculated according to the code clause 6.3.1 page number 32, where it states that the tensile strength is 0.9 times of A1 AN into Fu by gamma m1, where AN is the net effective area, and we know how to calculate the net effective area. It is B is nothing but the breadth of the flat minus D naught, where D naught is the diameter of the hole, which is given in the table 19 of the code, where you are going to refer for the standard clearance cases. For the diameter of the bolt is 16. In our case, it lies for 16 to 20 mm. We have got for 16 to 20 mm, we have got a clearance of 2 mm to be added to get the opening size of the hole, to be made in flat as well as in the flange of the section, where we want to make the hole here. It has to be, this value has to be added with 2 mm extra. It works out to be 18 mm. Now get me the value of the tensile force. It is 151.14 kiloton, which is greater than the F value. Safe. It is safe with respect to the slenderness ratio. It is safe with respect to the compressive force. It is safe with respect to the tensile force. Therefore, you can provide a flat of 50 by 16 mm. Earlier we had tried it. Now we are providing it. The size of the flat is 50 ISF 16. Now comes the connection details. The last part, designing the joints. In this case, we are going with bolted connection with 16 mm dia bolts. The number of bolts required on one side of the joint is given by force in the lacing bar by bolt value. They have the bolt 16, and we also know this how to calculate. Yes, whenever it is placed separately like this, it is a single shear, whereas in the previous video this was overlapped, therefore it was subjected to double shear. According to Glass, whatever the formula that was there, that has to be multiplied by 2. Now this is a case of a single shear. Previous video you observed it was double shear. This differences, if you note down, there is no problem. We'll assume that the thread is interfering the shear plane. Here the thread is interfering, therefore we'll take that value of n is equal to 1, and there is no value for the shank portion, it's 0. Gamma MB from the table, it is 1.25, and ANB, area of the threaded portion, is 0.78 times of pi d square by 4. For the shank portion, it is pi d square by 4 that you observed in the previous video. And all these things you have studied in the bolted connection in the second model. The VDSB value, the strength of one bolt in single shear is equal to 28.97 kilonewton. Next, you calculate the strength of the bolt in bearing, which is given in page 75, clause 10.3.4, where it is given as VDPB is equal to 2.5 into KB into D into T star Fu by gamma MB. T star is nothing but the minimum thickness of these two, that is flat as well as thickness of the flange. The minimum has to be taken here. Now in the previous video, we had taken the values, calculated all these values of E, P, E neglected, not applicable, so we just neglected it. We found out the values. Now in this case, to be on the conservative side, I am going to assume the value of 1 here to be on the safer side. I will take this value as 1 and calculate the value of the bolt in bearing VDPB. The thickness of the flange of the section is 13.6, and thickness of the lacing bar what we designed was 16 mm. The minimum is 13.5. Make use of that in the formula. T star KB, we have taken 1 on the concept of conservative side, got the value of 178.8 kiloton. The bolt value will be always the least of This VDSB and VDPB, strength of the bolt in shear and strength of the bolt in bearing for one bolt. It's 28.97 kilonewton. Find out the number of bolts, and that's equal to 22.98, that is the force in the lacing bar, by 28.97.79. Provide minimum one number of bolt on each side of diameter 16 mm of grade 4.6. So in the previous video we had stopped at this stage, but in this problem I am going to teach you how to design the tie plate. This tie plate will be designed with the same as what we are going to do it for the batten section. Now as far as possible it has been simplified here and try to make simple calculations. Now let us find out. This width of this one is very simple to calculate. It is nothing but equal to the spacing between the webs of the channel section plus the width of the flanges, which you can note down from the steel table, and it is 90 mm there. You can get the total width. Find out the depth of this one and the thickness. Okay. Now effective depth of the tie plate will be calculated here based on the number of bolts that we are going to provide. It is equal to back-to-back spacing of the channel plus 2 times the CYY value which you are going to get from the steel table, and this is worked out to be 24.4 mm, the CYY value for this section. It's true 68.8 mm is the effective depth. That will be the distance between the two bolts. I'll show you that later. The overall depth of this is equal to 2 times of this distance between the bolts and the minimum edge distance what you are going to give, 2 times edge distance, and the minimum edge distance is equal to 1.5 times the D naught value, that's 30. Add up and get the overall depth of the section. It's 330 mm. Overall depth is 330. Width is very simple. It's back to back width of the flange and the 2 times the width of the flanges. Back to back distance between the webs of the channel section and this one. It's 220 plus 2 times of 100. It's 420. Thickness is given as by the formula 1 by 58 times the back to back distance plus 2 times the G value from here to here. This distance divided by 50 will get me the thickness of the tie plate, and that's 8 mm. So we are going to provide a tie plate of size 420 by 330 by 810 mm. There is a thickness. Nominally you provide 2 bolts here, 2 bolts here. Go with the 4 number of bolts for the connection. Hope you understood the design of the lacing system for the 2 channels placed back to back with the bolted system. This is a bolted system. In the coming video we will go with the welded section. Same problem we can take. I can change the section or I can design the same section and design with the welding for the lacing system. Hope you understood this. If you like it, please do comment it in the comment box. If you are not subscribed yet, do subscribe now. Thank you very much.